Ladies and gentlemen, welcome. Imagine a room full of people where everyone speaks a different language. Chaos, right? The world of electronics is exactly like that. From Bluetooth to TCP or IP, our devices need a set of rules, a universal translator to understand each other. Today, we are going to introduce how these devices talk, listen, and understand. Why do we need these rules? Because of modular design. Look at this laptop and printer. They are separate islands. The laptop creates the data, and the printer consumes it. To bridge this gap, we need standardized communication. But how do we physically transport that data? Do we send it bit by bit or all at once? That brings us to our first major comparison. How data moves. First, let's look at parallel communication. Imagine a wide highway. Here, multiple bits of data, represented by these packages, travel simultaneously. It's fast because we move a lot of data at once. However, look at the infrastructure. It requires many wires, lanes. This makes it expensive and complex to route over long distances. Now, compare that to serial communication. Here, the data travels single file, one bit at a time, like ants in a line. Is it slower than parallel? Traditionally, yes. But it is incredibly efficient. We save space, reduce wires, and with modern technology, we can push these single lines to incredible speeds. This efficiency is why most modern protocols like USB utilize this method. Timing is everything, but there is a problem. When I send a bit, how do you know when to read it? In synchronous communication, we use a shared clock. See the big clock in the middle? It sends a pulse. On the tick. Now! Every time the clock pulses, the sender pushes a bit and the receiver grabs it. They are perfectly synchronized. But what if we don't have a clock wire? That is asynchronous communication. Here, the robots, devices, must agree on a speed before they start talking. This is called the Baud rate, for example, 9,600 bits per second. Since they don't share a clock, they rely on this pre-agreement to know exactly when to look for data. The data and the physics. Now, what exactly are we sending? We don't just throw raw data into the wire. We encapsulate it into a packet. Header. Like an address on an envelope, it tells us where it's going. Payload. This is the actual valuable information inside. Trailer. This signals the end of the message, often containing a checksum to verify that the data didn't get corrupted along the way. A quick technical note on the physical reality. Computers think in ones and zeros, but wires carry voltage. Sometimes this can be confusing. In protocols like RS-232, we use inverted logic. Surprisingly, a negative voltage represents a logical one and a positive voltage represents a logical zero. It's a reminder that the physical layer follows its own rules. Scalability and evolution. As our systems grew, we faced a challenge. Old standards like RS-232 were point-to-point, one wire for every device. Look at the building on the left. It's a wiring nightmare. The solution is a multi-drop network, shown on the right. By using a bus system like RS-485 or I2C, multiple devices can share the same cable. Scalable, efficient, and clean. We also evolved in terms of traffic flow. Half duplex, USB 1.1 or 2.0. Like a one-lane road. Cars can go both ways, but not at the same time. You have to wait your turn. Full duplex, USB 3.x. This is the modern standard. A divided highway where data flows in both directions simultaneously at super speeds. Specific protocols, I2C and SPI. Let's dive into the most common protocols you'll use. First, I2C, its magic lies in simplicity. 2 wires only. SDA carries the data. SCL carries the clock signal. It's elegant, but how do we differentiate devices? We use addressing. The master screams out an address, say 0x42. Only the device with that specific ID, the light sensor in this case, responds. The others simply ignore it. This allows us to daisy chain many sensors on just those two wires. If I2C is the polite conversation, SPI is the high-speed conveyor belt. It uses four wires. Look at the data belts: MOSI, master out, slave in, and MISO, master and slave out. They move data constantly. Instead of addresses, the master physically selects which slave to talk to using a slave select line. It's faster than I2C, but requires more wiring. Let's bring this to the real world with microcontrollers like the Raspberry Pi Pico. Here is a simple UART connection. One Pico transmits, TX, the other receives, RX. It's a direct chat, simple, reliable, and perfect for device-to-device communication. We also use this to talk to our computers. The Pico sends UART data, which is converted to USB, appearing as text on your monitor. This is how we debug code and see what our robots are thinking. In conclusion, a modern engineer acts as the conductor of this orchestra. In this final image, you see the Pico acting as the central brain. It speaks I2C to the temperature sensor, SPI to the display, and processes it all simultaneously. Understanding these protocols isn't just theory, it is the key to building the interconnected world we live in today. Thank you